Okay, so before finding the Laplace transform for different known functions, first we should define how to find Laplace transform, the definition of this transform. So, Laplace transform of a time domain function is given as continuous summation or integral, a definite integral from minus infinity to plus infinity of that function multiplied by e to the power minus xt. This is the definition. But we would hardly be using this definition in this course. Instead, we would be using some well-established results of Laplace transform to our convenience for this course, right? So, I think I should move on to that. The first function, right, which we would be using in this course is the unit step function. So how to define the unit step function? We would be using the notation of ut for it. So ut is equal to 1 for t greater than or equal to 0, and it is equal to 0 for all t less than 0. Basically, for every negative value of time, it is not defined, it is 0, and for every positive value, it is 1. So, graphically, if you want to see, simply this. This is t, and on this axis, I will draw ut. Let's say this is 1. So the value of function will be 1 for all values of time t, all positive values of time t, and it will be equal to 0 for all negative values. Right? So this is my unit step function. So you see this is a discontinuous function, right? So if you have a discontinuous forcing on your spring mass system, solving the differential equation itself would be challenging. But when we go on to the complex domain, the S domain, you'll see that the Laplace transform of this unit step function is quite simple. And you must also be remembering from your mathematics course, it is simply Laplace transform of this time domain function will be a function of s, as I have already told you, and this is equal to nothing but 1 upon s. We would directly be stating this, we have not derived this. If you are interested in derivation, you can look into your books. But as I said, we will be using mathematics, not studying mathematics, right? We would be using it as a tool in this course. Then the next function that we will be using in this course is the impulse function. And the impulse function, we would be denoting it by delta, and it is defined as graphical definition. For all negative values of time t, it is 0, right? At t equal to 0, it goes to infinity, and then for all other values, it is 0. So it goes to infinity here it is 0, and here it is 0. This is your impulse function. You can define it at other times also. Let's say you want to define it at this point, then it would go to infinity at this point, but then you will mathematically denote it as t minus t naught. And this is the value of t naught where it goes to. Right? But if you are writing delta t, that means at t equal to 0, the value of the function goes to infinity. Again, you should appreciate that in time domain, solving differential equations involving impulse function, I would say would not be very easy. It would be challenging. But you'll see the Laplace transform of this function, and it will very simply be equal to 1. So Laplace transform of impulse function is equal to 1. As simple as that. Right? So going into S domain really pays off.
Sir, is there any difference between unit impulse function and impulse function?
Unit